Bismillahirrahmanirrahim. In today's lecture, we will study about chapter 8, that is exhaust flow. In chapter 7, we have studied regarding combustion, what all is happening in the combustion process, whether it's a SI engine or a CI engine. Now, after the combustion, we have in or after the combustion, the process is known as exhaust process because the combustion took place and the power stroke is going on. At the end of the power stroke, we have beginning of the exhaust process. Let's see how this exhaust process affects the overall engine cycle. Now, exhaust process is covered in two steps. One is exhaust blowdown followed by the exhaust stroke. Exhaust blowdown occurs when the exhaust valve starts to open towards the end of the power stroke. When your piston is moving from TDC to BDC in power stroke, combustion has started, and somewhere at the end of the power stroke, your exhaust valve starts open. When exhaust valve starts open, your exhaust blowdown process started. So exhaust blowdown occurs when the exhaust valve starts to open towards the end of the power stroke, somewhere around 60 to 40 degree before BDC. So piston is moving down towards BDC and somewhere 60 to 40 degree means if at BDC we take it as 0 and TDC a 180 degree or other vice versa, then 60 to 40 degree. If it is 180 degree there minus 60, 120 degree before 120 degree, your piston starts, your exhaust valve starts opening. At this time, pressure in the cylinder is still about 4 to 5 atmosphere. So quite a high pressure because we have a peak value pressure at the start of the combustion and the pressure dies down as we have seen in PV diagram. And the temperature is upward of 1000 Ks around. Pressure in the exhaust system is about 1 atmosphere. It is after the exhaust valves, okay? That pressure there is about 1 atmosphere, but pressure within the combustion chamber, that is 4 to 5 atmosphere. And when the valves is open, the resulting pressure differential causes a rapid flow of exhaust gases from the cylinder through the valves into the exhaust system. So we have a exhaust blowdown. Now, as the pressure in the cylinder decreases during the blowdown process, the gas leaving will have progressively lower velocity and kinetic energy. Initially, when the valves are open, they will have a higher velocity and kinetic energy due to pressure differential. But with the passage of time, piston is moving down towards BDC, progressively lower velocity and kinetic energy will be experienced. If a turbocharger is located close to the engine near the exhaust valve, the kinetic energy gained in the blowdown can be utilized in the turbine of the turbocharger. So initially the pressure is high, temperature is high, the kinetic energy is high, the velocity is high. So that amount of energy is used, kinetic energy is used for drive the turbine of the turbocharger. Blowdowns takes a finite length of time as we know. The exhaust valve should be as large as possible, considering all other demands in the design of the combustion chamber. So the design of the exhaust valve is such like that it should have a maximum dia. A larger valve gives a greater flow area and reduces the time of blowdown. If we have a larger diameter valve of exhaust valve, it gives a greater flow area and reduces the time of blowdown. This allows for a later exhaust valve opening and a longer expansion stroke with less lost work. So it has an advantage of this, that this will allow a later exhaust valve opening and a longer expansion stroke or power stroke with less loss of work. Now, modern engines have two exhaust valves per cylinder, or there may be three or four depending upon the types. Generally, in many modern engines, we have two exhaust valves per cylinder, with the flow area of the two small valves being greater than the flow area of one larger valve. So instead of one larger valve, we are using two smaller valves, but their combined area is greater than the area of a one larger valve. This gives added design flexibility. So this larger area of combined two exhaust valves gives added advantage of design flexibility and to complexity for fitting the exhaust valves into the existing combustion chamber space. Now, slow speed engines can have very late exhaust valve opening. The valve problem is compounded by the fact that the intake valves should be totally open at TDC when the intake starts. Now, during we have a after the blowdown, the piston starts moving from BDC to TDC. Now the exhaust stroke is happening there. And before the piston reaches TDC, the condition is this, the intake valve should be totally open so that we have fresh intake inside the combustion chamber. Because of the finite time required to open this valve, it must start to open 10 to 25 degree before TDC. So the piston is approaching from BDC to TDC. So 10 to 25 degree before TDC, your intake valve should be starts opening. A period of 15 to 50 degree of the engine rotation when both the intake and the exhaust valves open. So there will be a period, overlapping period, and this is called valves overlapping. And this valve overlapping period is 15 to 50 degree of engine crankshaft rotation. Now, during valve overlap, there can be some reverse flow of the exhaust gases back into the intake system because the intake from the intake valve is open and the air or air-fuel mixture is coming to the combustion chamber at a pressure of 1 atmosphere. But exhaust gases are moving out with a high pressure. Still, there will be a high pressure. So the exhaust gases will also move towards the intake valve and try to reverse flow in that direction. When the intake process starts, this exhaust is drawn back into the cylinder. So when the fresh amount of air fuel mixture is coming in, that exhaust gases which are escaped from the intake valve is drawn back into the cylinder along with the air fuel charge. This results in a large exhaust residue during the rest of the cycle. So this coming back of the exhaust from the intake valve is creating a large exhaust residue during the rest of the cycle. This backflows of the exhaust gases is a greater problem at lower engine speed, being worse at idle condition. So this backflow of exhaust gases is a greater problem at lower engine speed, being worse at idle condition, because at most low engine speed, the intake throttle is at least partially closed, so creating a low pressure in the intake manifold. This creates a greater pressure differential, forcing exhaust gases back into the intake manifold. Some engines have a one-way reed valve at the exhaust port to keep exhaust gas from flowing back from the exhaust manifold into the cylinder and intake system during valve overlap. So in modern engine or in some engine, we have this one-way reed valve, and the function of this one-way reed valve to is to stop the flowing back of the exhaust gases from the exhaust manifold into the cylinder and intake system during the valve overlapping. Now, engine equipped with turbocharger or supercharger often will have intake pressure above 1 atmosphere. Now, if we are having a turbocharger or supercharged engine, that the intake pressure is always above than 1 atmospheric pressure and are not subject to exhaust backflow. So another negative result of valve overlap is that some of the intake air-fuel mixture can short circuit through the cylinder when both valves are open, with some fuel ending up as pollution in the exhaust system. So the pressure coming air fuel mixture or air coming into the cylinder is high because of the turbocharger and the supercharger. So that pressure of, of air fuel mixture will short circuit the cylinder and it will go to the ends up in the exhaust system. So that it will create a pollution or in the exhaust system. Variable valve timing, which is starting to be used on some automobile engine. It decreases the problem of valve overlap if we have a variable valve over timing. So decreases the problem of valve overlapping. At low engine speed, the exhaust valve can be closed earlier and the intake valve can be opened later, resulting in a less overlap. Now exhaust process. Let's see on the x-axis, we have the strokes TDC to VDC. This is your power stroke. Then this VDC to TDC, we have an exhaust stroke. And from TDC to VDC, we have an intake stroke. On crank angle is on x-axis and exhaust mass flow is on your y-axis. So exhaust gases flow out of the cylinder through the exhaust valves, showing blow down and exhaust stroke. Possible reverse flow back into the cylinder may occur during valve overlapping. So piston in the power stroke is moving from TDC to BDC somewhere here. Pressure mass, your exhaust valve starts opening here, somewhere here before BDC. So, and how much is the degree? We have studied 60 to 40 degree before BDC. So 60 to 40 degree before BDC, your exhaust valve starts opening. So exhaust mass flow is going on. This is your exhaust blow down. When the piston reaches BDC, your exhaust valve is fully open. Okay. So then we have a variation of this exhaust in the exhaust stroke. And somewhere here 15 to 20 to 15 to 25 degree before TDC, your intake valve starts opening. So we have this dip here. This is the valve overlap period. So in this valve overlap period, we have possible reverse flow back into the cylinder may occur during valve overlap. And then we have 1 atmosphere in which here the exhaust valve is fully closed, only the intake valve is open. So we have 1 atmospheric pressure here. Now exhaust valves, as we know from chapter 6, valves are made smaller than the intake valve. Intake valves is always 10% more in dia than your exhaust valve. Although the same amount of mass must flow through each. The pressure differential across the intake valves of a naturally aspirated engine is less than 1 atmosphere, while the pressure differential across the exhaust valve during the blowdown can be as high as 3 to 4 atmosphere. Now to note some few words regarding temperature. Temperature of the gases in the exhaust system of a typical SI engine will average 400 to 600 degrees Celsius. So the average exhaust temperature lies in the range of 400 to 600 degree Celsius. This drops to about 300 to 400 degrees C at idle conditions, because at idle condition we don't have a full power. So this range is reduced from 400 to 600 to 300 to 400 degrees Celsius and goes up about 900 degrees Celsius at maximum pressure when we are wide open throttle and we have a maximum power we are receiving. So the temperature goes up till 900 degrees Celsius. This is about 200 to 300 degrees Celsius cooler than the exhaust gases in the cylinder. In the cylinder, the exhaust gases temperature is high, so this is the exhaust temperature of the gases in the exhaust system is 900 degrees C at maximum pressure, and this is 200 to 300 degrees C cooler than the exhaust gases in the cylinder. When the exhaust valves open, the difference is because of the expansion cooling. So this difference is due to the expansion cooling. All temperatures will be affected by the equivalence ratio of the original combustion mixture. So equivalence ratio plays an important role in the combustion and the temperature inside the combustion chamber. Now, talking about the CI engines, the average temperature in the exhaust system of a typical CI engine will be 200 to 500 degrees C. This is lower than SI engine exhaust because of the larger expansion cooling. So because of the larger expansion cooling, we have a range in SI engine is 400 to 600 degrees Celsius, but here in CI engine it is 200 to 500 degrees Celsius, and that is due to larger expansion cooling. That occurs due to the high compression ratio of a CI engine, and that larger expansion cooling is due to the higher compression ratio of a CI engine. If the maximum temperature in a CI engine is about the same as in the SI engine, the temperature when the exhaust valves open can be several hundred degrees less. The overall lean equivalence ratio of a CI engine also lowers all cycle temperature. So due to lean equivalence ratio, CI engines have lowered all cycle temperatures. Now, part of the exhaust systems are exhaust valves, exhaust manifold, turbocharger, EGR, exhaust gas recycles, catalytic converter, tailpipe, and muffler. Less catalytic converter, we will talk about all these parts and we will cover this catalytic converter in our next chapter. Now, the exhaust manifold. After the exhaust valves, we have the exhaust manifold. After leaving the cylinder by passing out of the exhaust valves, exhaust gases pass through the exhaust manifold, a piping system that directs the flow into or one or more exhaust pipes. Exhaust manifolds are usually made of cast iron. So they are usually made of cast iron and are sometimes designed to have close thermal contact with the intake manifold. And sometimes they are designed to have close thermal contact with the intake manifold. The reason is this is to provide heating and vaporization in the intake manifold. So it provides heating and vaporization in the intake manifold. Chemical reactions are still occurring in the exhaust flow as it enters the exhaust manifold. So because the temperature and pressure is still high and its chemical reactions are still occurring due to this high temperature and pressure in the exhaust flow as it enters the exhaust manifold, with carbon monoxide and fuel components reacting with unreacted oxygen. These reactions are generally reduced because of heat losses and the lower temperature after blowdown. The temperature goes down, then these reactions will greatly reduce. Some modern engines have insulated exhaust manifold that are designed to operate much hotter and act as thermal converter. So in some modern engines, we have insulated exhaust manifold, and that insulation provides high temperature to operate much hotter and act as a thermal converter to reduce unwanted emissions in the exhaust system. So the advantage of this is to act as a thermal converter to reduce the unwanted emission in the exhaust gas. Now, tuning of the exhaust manifold and another important factor. The runner lengths of the exhaust manifold can be tuned to give an assist to the gas flow because the flow is a pulsed flow. Pressure waves are set up in the manifold's runner. Some high performance engines, variable tuning is used with runner length dynamically adjusted as the engine speed changes. So with the engine speed changes, the runner length, the piping length is dynamically adjusted. Other engines use dual runner of different lengths. So if we have a 6-cylinder inline engine, first cylinder exhaust manifold will be different, and rest of the 3-cylinder will have different piping arrangement. Automatically switching the exhaust flow to the runner that is best tuned for that speed. Now, next part is turbocharger. Turbocharger should be mounted as close as possible to the cylinder exhaust ports or walls so that the turbine inlet pressure, temperature, and kinetic energy can be as high. So it should be as close as to the exhaust manifold. Because of the limited pressure drop through the turbine, it is necessary for it to operate at a speed upward of 100,000 RPM, as we have studied previously, to generate enough power to drive the compressor. So these high speeds, along with high temperature, corrosive gases within which the turbine operates, creates major mechanical and lubrication design challenges. So there is a drawback also, that this high temperature and high speed corrosive gases within which the turbine operates creates major mechanical and lubrication design challenges. Many turbochargers have a bypass which allows exhaust gas to be routed around the turbine. So they have some bypass arrangement in which the gas is routed around the turbine. This is to keep the intake flow from being overcompressed when engine operating conditions are less demanding. So the reason for having this bypass is to keep intake flow from being overcompressed when engine operating conditions are less demanding. The amount of gas passing through the turbine is controlled according to the engine needs. Now, exhaust gas recycle, EGR. Modern automobile engine uses exhaust gas recycle to reduce nitrogen oxide emission. Some gas is routed from the exhaust system back into the intake system. This dilutes the intake gas mixture with non-combustibles, which then lowers the maximum combustion temperature and consequently reduce the generation of the nitrogen oxides. So in modern automobile engines, uses exhaust gas recycle to reduce nitrogen oxide emissions. Nitrogen oxide emissions. Some gas is routed from the exhaust gas back into the intake system. This dilutes the intake gas mixture with non-combustibles, which then lowers the maximum combustion temperature and consequently reduces the generation of the nitrogen oxide. The amount of EGR can be as high as 15 to 20% of the total mass and is regulated according to the engine operating condition. So the range for the EGR, the amount of EGR can be as high as 15 to 20% of the total mass and is regulated according to the engine operating conditions. Under some conditions, such as starting or wide open throttle, no EGR is used. So in these conditions, no EGR is used. And in addition to the reducing the maximum combustion temperature, EGR increases the intake mixture temperature and affects fuel evaporation. So EGR these two functions also. Now, the last tailpipe and the muffler. After exiting the catalytic converter, we will study this in our chapter 9 when we will study the emissions and pollutions. So after existing the catalytic converter, these catalytic converters are used in the modern vehicle. Previously, there was no concept of these catalytic converter. Now in modern vehicle, all modern vehicle, we are having this catalytic converter. Exhaust gases flows through a tailpipe and ducts the flow away from the passenger compartment of the vehicle and vents it to the surrounding. This is usually under and out of the back or side of an automobile and often upward behind the cab of large trucks. So it depends if it's a vehicle, it's a car or sedan or something SUV. The tailpipe goes till to the trunk of your vehicle. But if we have a large truck, it's usually goes upward behind the cab of a large truck. Somewhere in the tailpipe section, there is usually a larger flow chamber called the muffler. This is a sound chamber designed to reduce the operating noise of the engine, most of which is carried out with the exhaust flow. Now, mufflers are used two general methods for sound reduction. One method absorbs the energy of the sound pulses by flow through the porous medium. So one method to reduce the sound reduction is to absorb the energy of sound pulses by flow through a porous medium. Other mufflers reduces sound by cancellation of the waves. Instead of fully dampening all engine noise, some mufflers designed to give a louder, sporty sound. So it depends. Now, up till now, this was for four-stroke engines or SI engines or CI engines. Now, what about two-stroke cycle engines? The exhaust process of a two-stroke cycle engine differs from of a four-stroke cycle engine in that there is no exhaust stroke. As such, blowdown is the same, occurring when the exhaust valves open or when the exhaust slot is uncovered near the end of the power stroke. This is immediately followed with the intake process of a compressed air or air-fuel mixture. So, as the pistons uncover the exhaust port or the exhaust valves open, you have an exhaust blowdown. And immediately after this is followed with an intake process of the compressed air or air-fuel mixture. As the air enters the cylinder at a pressure usually between 1.2 and to 1.8 atmosphere, it pushes the remaining lower pressure exhaust gases out the still open exhaust port in a scavenging process. So scavenging process is there, air fuel mixture which is coming in two-stroke engines